All right, so here's what we're trying to do. And I'm going to review some problems. Remember, if you got a mechanism, it's always by the slow step that the mechanism gets determined. And you use your stoichiometry if that slow step is the first step. Here is an example of that. And uh, I've got this reaction, 2 NO2 means this, that's the overall reaction. Here's the mechanism that's slow then fast. So since this is the slow step, I just use the stoichiometry, the first step, and that's what my rate would become. Right, it's double order, double order. Second order as opposed to nitrogen dioxide. All right, now here is a bit of a trickier one, and because as you'll see it play out, here's my reaction. Now here, the second step is the slow step. So the first thing I want to do is write my rates for the first two steps, or no, not the first two steps, for the fast equilibrium step. And I can do this because at equilibrium, they're going to be equal, all right? And then I want to solve for any intermediates. If you look at the reaction, you can see that my intermediates are those guys, those oxygen radicals, free radicals. So I want to solve it for oxygen. And here's where things get interesting. To get oxygen out of alone, I had to divide by this. Got to divide both sides by this. All right. And that's what this becomes. These would cancel, and I'm going to get the concentration of O is equal to K1 over this, the concentration of O3 divided by the concentration of O2. And this is equal to another way to write this is K1, K inverse concentration O3, concentration O2 negative 1. All right, where this means it's in like that. All right, now the next thing to do is to write the rate law for the slow step. So rate is equal to K2 in this regard. There isn't a 2 there. I forgot to label it. K2 times the concentration of ozone times the concentration of oxygen. And then I'm going to substitute this into this equation. Take this whole thing and plug it in right there. So that would be equal to, remember, I'm taking and then simplifying. So rate would be equal to K2 times concentration of O3, K1 over K inverse 1, concentration of O3 divided by the concentration of O2. All right. And now I want to combine like terms. I would bring all my K's to the front. K2 times K1 divided by the observed rate of the reverse reaction, K inverse 1, O3 squared, and O2 negative 1 equals rate. And then just to clear things up a wee bit more or make things a little more neater, I write K and there's that, which is the observed rate constant. All right, that's what this is. And just so we're clear, you could also write this at like this. Now, the fact that I've got a negative order means that in the presence of oxygen, the rate of this reaction is decreased by an order of 1. So for uh, the more O you have, the slower this reaction is going to go. So there are negative orders. And uh, the overall reaction order is going to be 1, all right, because 2 plus negative 1 is 1. I kind of feel that this is the way it works out because we want ozone in the air, so we don't want to get rid of ozone, and that's why it's kind of like there's lots of oxygen in the air. And then just so we're clear, K prime, or K observed, the rate constant, is equal to K, where these are the observed rate constants from the first from the first from the mechanisms here. Okay, but that's my answer. You could write it like this, or you could write it like that. All right, either way is fine. Okay, one more problem, and this problem is also going to need us to do some fancy dancy. This is a 3-time mechanism. All right, the first step isn't the slow step. The second step is. This is a little bit out of focus. That's K1, and I'm a little bit sloppy, but anyways. So here we go. First step, write the equilibrium. So K1 H2 equals K inverse H, and that's going to be raised to the squared. All right. Now this is interesting. This is different because H is our intermediate. You can see it right there. All right, that gets gobbled up on the next step, and so we need to get rid of this. All right, and we solve this for H. All right, because our rate law, and I'm going to skip to the third step. Our rate from this third step is equal to K2 times the concentration of H times NO, like that. All right, so we need to solve this for H to plug it into this equation. So let's solve this for H. All right, and I'm just rewriting it so that it's easier to follow. I hope too for you. So I'm going to divide both sides by K1, or K inverse minus 1. These are going to cancel, and I'm going to be left with this. All right. All right. Now I've got a squared. So how do I get rid of a squared? I have to take the square root. So the square root, so this is going to be raised to the half power, and this is going to be raised to the half power, and then that's just that. All right. So now I plug this whole thing into this equation, and I'm going to get rate equals K2 times K1 half, and then concentration H2 squared. Oh, sorry. Concentration of H2 to the half times the concentration of NO2 squared. All right. Okay. Now this is interesting because what this means is it's still a positive relationship, but if you quadruple this, you'd raise it by 4 to the half, it'd be 2. So you quadruple, you double the rate. All right. Now this whole thing can become K prime, or the observed rate constant, H to the half, and NO2 to the second order. All right. Now the observed rate constant would be this whole thing written out. I kind of ran out of room, but this K observed rate constant would be K2 times K1, or the square root of these two divided by each other. All right. But that's my rate constant. And remember, this half means if I quadruple the concentration, I would take that would only double the rate. All right. It's not quite a order one, but halfway there. All right. Hope this has been helpful.